Okay. All right. Well, this is going to change the world. The things that are about to happen here shortly. So I'll give you kind of an overview. I've been involved because I'm at Hightower. I'm with Engineer, and appreciate you guys inviting me here to come and speak. I hopefully this will give you some insights into what's about to happen. Our world is at an inflection point, and we're going to be able to do things that we never were able to do in the past. So I've been involved in wireless communications and machine-to-machine and mobile data for over 30 years now. And the last 4 or 5 years, though, I found out about a low-power technology called, a low-power wide area network technology called Weightless. And that started me on this road to keeping up. Mary and her group in Dallas, the IEEE over there, invite me back every 6 months or so to give an update on what's going on in the Internet of Things, particularly low-power WANs. So this is my 6-month mark here, so I'm going to be able to give an update and an overview of what's going on. So I'm going to give kind of a level setting so everybody understands what the Internet of Things is about, how it's moved from machine-to-machine communications into Internet of Things and how that's different, and then what the 3 basic components are of the Internet of Things. And it's a very rich environment, each one of those things, but there's a lot of, I'm going to break it down and then we'll talk about the wireless part in particular, and the connectivity part. So low power WANs is that connectivity part that I'm really focused on, and then I'll talk about Ingenu, my company, and how we're doing the low power WAN technology and implementing it. So the historians look at Internet of Things and machine-to-machine communications, and they say the actual first machine-to-machine system was the telegraph back in 1832, and it was put in, and at first they didn't know what to do with it, but it was able to remotely monitor another device and then control it. So that fits the definition of a machine-to-machine system. Then they added Morse code onto that, and then it took off. And Nikola Tesla realized that the technologies that were coming online, even back in his day, one day would interconnect everything in the world, and we would have a device we could have in our pocket and control things that we never could control remotely. So he was a visionary kind of guy, very interesting. So we all know about machine-to-machine, but we may know it by different names. So oftentimes people would call it telemetry or SCADA. Industrial automation or telematics, talking to cars, and then sensor networks. And so that's all lumped into the area of machine-to-machine. So that typically dealt with a domain. So only the cars, or only the sensors in an industrial plant, or maybe the electric grid for your SCADA kind of stuff. So it was one domain. That's a machine-to-machine type of system. And the technologies that were used were wireline, microwave, private radio, Wi-Fi for short range kind of stuff, satellite if you wanted to do big coverage but it had to be outdoors, and then cellular. Cellular actually was a very popular, and has been a very popular use or technology to enable machine-to-machine communications. What's about to happen though is we're going to be moving from individual domains to the Internet of Things, which will take all these different domains of information and bring it back and allow us to be able to see a better view, a better vision of the environment that is out there. Because we're going to be able to see what the weather is like, whether the electric grid is working or not working, whether people are at home or not, whether people are on the road. There's going to be lots of information we'll be able to collect and bring back and do things with that information that we weren't able to do in the past. But what's going to happen, it's going to be an inflection point. Now we've had many inflection points along the way. So Andy Groves wrote about this in his book, Only the Paranoid Survive, which I love the title. Jack Kilby created the integrated circuit back in '58, and that changed the world. We now have the electronics that we have today because of the basic ideas that he created, that when everybody else was on vacation, he was working on that at his lab. Then of course in '84, the Bell monopoly was disbanded, and that led to incredible amounts of innovation in the communications world. And then the early 80s was the personal computer, the 90s was the internet became available to the masses, and in 2007, Steve Jobs changed the world when he came out with the smartphone, a whole different thing. But what's going to happen now is an inflection point that's going to dwarf anything that's come before. What we're going to see is, right now we have maybe 10 billion devices in the world connected with machine-to-machine kind of technologies. We're going to have between 20 and 50 billion devices connected in the next 5 to 10 years. It's all over the place, it depends, but the point is, we're going to have a tremendous amount of devices connected back into computer and applications on the back end, and we'll be able to do things that were never possible in the past. So, this is a very complex and very rich environment that we're in, but I break it down into 3 areas. So you got the devices that are in the field, so you got your endpoints out there, sensors and actuators. And then you've got the connectivity part. Typically it's wireless, but it can be wireline, it can be short range, it can be long range. And then you've got the back-end systems. And that can be the computer systems, the storage systems, the cloud, analytics, big data, and networks of their own to be able to transfer information around among themselves. What I'm going to focus on today is the connectivity part, and particularly on low-power WANs. But the connectivity part in the past, cellular was a great way to do it. Their 2G networks were a great way. There's like 30 million devices in the United States that are connected on cellular on their 2G networks right now, so that you can control and operate and manage devices that are out there in the field if you have long-range needs. If you have short-range needs, then the short-range technologies, Wi-Fi, Mesh, Zigbee, Bluetooth, low energy, those are all very popular methods to be able to talk in a relatively short area, short range, within a manufacturing plant or a home or a condensed area. And then you've got private radio and microwave. They're useful, but they're not ubiquitous. So they have purposes, but kind of limited. And then you've got satellite, which gives you a great footprint, but it doesn't penetrate into buildings. It doesn't go into the basements, into the equipment vaults where a lot of control and command or control and monitoring needs to be done. So what I found was, back about 4 years ago now, I was reading up on some technologies called weightless, actually, at the time. Weightless is a standard that was created out of the UK. A professor worked for their FCC, Ofcom in the UK, and realized that the TV white space, our broadcast channels here in the United States, we have a TV channel that transmits from channel 21 and channel 23. If nobody's on 22, that's white space. And he realized we could take advantage of that white space, transmit at low levels with special protocols, and not interfere with our TVs on either side on 21 and 21, then that could be useful for connecting all these machine-to-machine and the Internet of Things devices that we need to talk to. And he realized then, there could be billions of devices that need to be connected. And this would be a great way to do that. A lot of capacity in that white space area of TV broadcast channels. And those channels are the same thing all around the world. The problem was, only the United States and the United Kingdom have agreed or passed the laws to allow low power transmissions on those TV white space frequencies. The rest of the world is way behind. So he abandoned that, and other people have filled the void. So the other folks have thought about what other frequencies that are available that they could go into and be able to transmit low power but get long range. By being low power, they use the battery, low power consumption, so their batteries would last a long time. A lot of these devices are in harsh, remote areas that you don't want to go visit on a regular basis. You want to put something in, you want it to last for 10 years. So most of the low power WAN approaches are such low power that you can operate with battery for over 10 years. The other characteristic of low power wide area networks, they need to be low cost in their infrastructure so that you can put in a lot of base stations, a lot of access points, they call it a lot of times. You want to be able to put in this infrastructure out there at a relatively low cost. Cellular is very expensive. When you start putting in these base stations and cell sites at the tower sites, it gets very, very expensive very quickly. So they needs to be low cost in its infrastructure. The systems, however, need to be very scalable, because we're talking about billions of devices that are going to be added to the network. And then it needs to permit mobility. And there's two kinds of mobility, and so some of them will support both, some will support one or the other one. One mobility is where you install a remote site, it's stationary, but you decide to move it to another location, another country even, and then you tell it rescan and connect to that network there. That's one form of mobility. The other is true You got a rail car, you got a vehicle, you've got a container, a cargo, whatnot, traveling along. You want to be able to monitor what's going on with that. A true mobility application in that case. And it needs to be reliable. It can't just transmit and you hope it makes it. So if it's going to be a good, dependable, low power WAN network, it's got to meet this criteria. So cellular does a pretty good job. So, and they're going to have a place to play. There'll always be people that will want to use the cellular network for whatever reason. I'll talk about some of the pros and cons of the cellular network in the near future, because things are changing dramatically in the cellular world. Then the short-range technologies, Wi-Fi, Bluetooth low energy, Zigbee, mesh, all those short-range technologies will have a place to play as well. But the big users of connectivity are going to be the low-power WAN technologies. And it depends on who the analyst is. It'll be between 60 and 80% of all connections are going to be using the low-power WAN network and technology. And in fact, when they looked at the requirements of a remote site to transmit data about its status, what it's monitoring, what's going on at that location, they found that 86% of all those remote devices that we're going to connect require less than 3 megabytes per month of data transmission. So that's why low power WANs would be a great fit for that, because that's what they're designed for. Not the cellular high bandwidth requirements that our smartphones have. That's what the cellular guys are really, that's where they make their money. That's where they're putting their money and their technology focus on. The low power WAN guys, they're going to enable short messages, but billions of those messages a day, or sometimes quite often. But they're only going to be 3 megabytes per month for each of those devices. It turns out 76% require less than 1 megabyte. So there's that's a great fit for low power WANs. Now, I want to talk a little bit about the different players in that area. There's two kinds of technology that's pretty much being applied, except for the cellular guys, and I'll talk about them separately. But the low power WANs fall into two categories. One is narrowband, either narrowband or ultra narrowband. And so they put all their energy in a very narrow part of the spectrum, and they use that energy to get distance and penetration, and to punch through the interference that's in these environments. Now, most low power WAN guys are in the ISM bands, industrial, scientific, medical bands. They're restricted bands, but you can use them if you stay under the power rules and duty cycle, meaning how often you can transmit in that frequency range. So that's one way to do it. They put all the energy to the highest level that they can, and they concentrate everything and all the signal that they've got to punch through. The other guys are spread spectrum. So you see the hump here. They're actually taking the signal, spreading the signal out over whatever range that they can, and it's in the noise. It's below the noise floor. And they're able then to send it out, stay within the rules, and then reconstitute it at the received end and create the communications link that way. So those are the two different ways that most people are doing that. So Sigfox, if you've been listening, you may have been paying attention and seen this before. Sigfox has been around for 4 or 5 years, and it was created by a French engineer. He says, I see that the cellular guys are eventually going to have to change, and this low power WAN stuff is they need a technology and a way to get their information back and forth. So he quickly took the idea of ultra narrowband. So he's in the spike category, and he went into ISM bands, 868 in Europe and 902 to 928 here in the United States, and then you got 433 and 169 and some other frequencies like that are possible to apply this technology. It's a very simplistic technology. It doesn't have very much security in it. It is only 100 bits per second upload, and you can only do 4 downloads, confirmations to it a day. And sometimes in some systems, in some nations, regions, you can't even do that. So it's basically a one-way system, and he doesn't have any kind of acknowledgement a lot of times, and he doesn't listen to what else is going on in that frequency. So Sigfox transmits their signal 3 times from the remote device and hope it gets through. And it's not a very clean way, not a very reliable way to communicate. But he's done a great job at marketing. He was one of the first companies to get out there. They're going to put a public network in. He's going to go into 60 countries, he says, and in the next 5 years, and they're already planning on doing 100 cities in the United States, 230 cell sites. That's a heck of a lot of infrastructure that they're putting in for a system that's not very, so we'll have to wait and see. It's not tested. That's the whole thing here with a lot of these low power WAN technologies. They've not been tested in the real world to confirm the theories and the ideas that the engineer that developed it has come out with. So we'll have to see. But he has received over $150 million from 14 different sources. So he's got money to work with. So we'll see how that all works out. So the other people, these people are very good technology. Again, they haven't tested this in real world extensively, so we're waiting to see. Their business model is different though. Instead of putting in a public network like Sigfox is doing around the world, they're selling base stations to people to put in private networks. Now these networks may become public. There are several cities in Europe that are built up enough that they're going to allow it to be public access to the system. But the idea is that it's individuals and groups that are doing this will eventually come together with alliances to create public kind of access. It is in the spread spectrum realm. They use a derivation of the chip spread spectrum technology. It's okay, it's pretty good. It doesn't increase the distance that they can transmit their signals. It is two-way, so they've got the ability to do acknowledgement, and that's good. It is low power consumption, so they can handle, their devices can last 10 years or so, in some cases. Now I'll explain why sometime. At the physical level, the chip level, that's proprietary technology created by Syntec. Syntec will license the IP to other manufacturers to create. So that's an issue. There's not a generic form of that physical layer to use. But the MAC layer above that, for all your control and signaling and everything, that's open. And so IBM donated their technology. Other people are creating their own ways to manage the physical layer. So that's interesting. It's creating a lot of opportunity for innovation. Now, the reason why I say in some cases the battery can last 10 years, they have 3 classes of remote devices. One class is where the remote device senses something happens, an exception takes place, whatever, for whatever reason, that remote device, endpoint, transmits up and it waits for a few moments to get an acknowledgement back and it goes back to sleep. So that one can last 10 plus years. The next class is it sees something, it transmits, it listens, and then it goes to sleep, but then it wakes up periodically on a schedule and says, do you have anything else for me? And then it goes back to sleep. So that can last at least 5 years and maybe longer. The class C, however, this one is a remote device listening all the time. And when it needs to transmit, something happens at the remote site, then it transmits, it turns off the receiver, and transmits up. That one needs to be on the grid. It's got to either have a very large battery or some sort of way to replenish the battery that it's using. But they give you a lot of capabilities there. So LoRa is a pretty interesting technology. It just needs to be tested out and proven out to see if it's going to work. There's concern that the frequency bands in the ISM, 868, 902 to 928, and some of the other bands are so narrow and so restricted that if you start putting multiple systems in those bands, there already is a lot of garbage in those bands right now, then they're going to kill each other. There's some cases they don't play nice together. And their security, there's a real concern about their security. There's not a whole lot. Sigfox has nothing, and LoRa has a little bit, not very much. So that's going to be, after last Friday, that's going to be a problem. I'll talk about that more in a moment. The other player, so Weightless W for white space came out 4 years ago. UK, US approved the rules, but nobody else in the world did. So they Weightless abandoned the Weightless W. They actually put it on the shelf right now. And they said, okay, what else is out there that we could get behind as an open standard? That's their claim, is that everything they've created is open. Any manufacturer can take the ideas, the technology, the IP, and create devices using this technology. So a company called Enwave said, we'll donate our IP, and you call it Weightless N, and anybody can take the technology and create product and systems for that. So they've created an open standard. It is on the ultra narrowband, the spike type. It is two-way to an extent. Their issue is they started out one way, they've added two-way, but there's an imbalance in the link budget between the up and down. So it's not as reliable as it needs to be. But they're working to make that as good as possible. It has applications in certain situations. It's not good for just anything. You got to be careful when you design your system. It is in the sub-gigahertz, the 902, the 928, and the 868, all those frequencies down there. It does frequency hopping, and it has some security built in, 128 AES encryption key to it. So not bad, interesting. Their US operations are based right there in Dallas with us. A good friend of mine is the CEO, COO, and CFO of the company. So they're making some headway in penetration in the United States. But they're UK based. Now, this is the big gorilla. This is the cellular's answer to the fact that 2G is going away. The problem is there are 800 carriers in the world. This 3GPP group is their standards group. It's driven by not only the carriers, but the manufacturers of the equipment that is sold to the carriers. So it's a real interesting interaction between the people in this standards group. Normally it takes years to be able to come up with a standard. They recognize that the low power WAN and the requirements for Internet of Things is going to take off here shortly, and they're going to miss the boat if they're not careful. They already have a couple other standards out there. That's the nice thing about standards, you got plenty to choose from. So in their case, they have LTE-M, they have extended coverage GSM, and another variation, and then they've got NB narrowband IoT. Looks like they're going to hang their hat on this. This will be the one that can compete against narrowband technology. Problem is, because they needed to rush it through and get something out there as quick as possible to respond to what's happening with the low power WAN initiatives, they took very simplistic radio environment assumptions and created their standard. It's still not been tested in the real world. They're just now deploying test systems out there to see how well it works. What they're going to find is the radio environment, even though the carriers own the frequencies, there's still a lot of harmonics and stray signals and garbage in those bands they have to deal with. And particularly in an urban environment, they're going to find that their assumptions were not robust, not strong enough, so their system is not robust. They're going to have to go back and do some rework on their standard, we believe. The other problem with their standard is that cellular systems, they make their money off of smartphones. That's what they're going to support. So they put priority for the smartphone traffic in this standard. If the smartphones need the capacity, if they take it away from the Internet of Things, the NB-IoT approach. And then you have to wait with your device until all the traffic gets cleared before they start transmitting. And so you have low latency issues. It will not be low latency in a lot of cases. And their other basic thing is that the cellular standard, collects data and schedules the transmission of that data. So that's another addition to the latency issue that they have. So there's a lot of things that need to be analyzed, understood, and tested in the real world, and then modified. They will get there. These guys are the big players. I believe, based on all the research and things I've been following for the last 4 years, there'll be two standards that become the key ones that you use. It'll be the cellular NB-IoT, and it'll be the RPMA, the Ingenue technology I'm going to talk about in a moment. 800 carriers around the world. There's a lot of money out there. They're going to find a way to make it work. And they haven't tested the battery either until they understand what the impact is of the environment on their protocol. They won't know how long their batteries can last. So there could still be a problem with that. So Ingenue is a technology that's actually been around since 2008. These guys came out of Qualcomm. So if you know anything about Qualcomm, out of San Diego, and they created the CDMA standard that the cellular guys use. and CDMA and the protocols that came on beyond that focus on giving smartphones and the cellular networks high-speed data communications and able to handle the capacity of the smartphones and the data requirements that they need. Two engineers out of Qualcomm left in 2008 and said, we're going to take the CDMA technology and we're going to modify it though. We're going to look at what the machines need. They don't need a lot of information. As we saw, 1 to 3 megabytes is what most of them were going to require, but there's going to be billions of these messages, billions of these devices out there. Excuse me. So they modified, they took their theories and they went to San Diego Gas and Electric, who's right there in their backyard, and said, guys, you know, we have this idea, we want to test it out. And they said, sure. And so for 3 years, 300 person years of testing, they took their devices, their prototypes and whatnot, went through the San Diego Gas and Electric system, testing out the different theories. So some of the theories were great. They were able to do things that they thought they should be able to do. And then some things just surprised them. They said, holy cow, what? In the real world, our theory isn't working like it needs to, so they had to rework it. But after 3 years or so, they not only created a highly reliable system that communicated over their frequency band that they chose, and I'll talk about that more in a second. It's a very unusual choice, but it's turning out to be a wise decision. They created a very reliable system that's been fully tested and banged on and improved along the way. But it also became a highly secure system. The utilities will not allow communications over any network they're responsible for if it doesn't meet FIPS and NIST requirements that the utility players are required to fill. So at the time, the engineer said we were just getting beat up by the utility about our security, but now we're glad we did because it helped us to improve and create a very reliable product. So that was 2008 to now. So last year, they installed 38 private networks. After they did San Diego Gas and Electric, they got Southern Cal Edison, then the oil and gas industry picked them up. They put a system in Nigeria here about a year and a half, about 2 years ago, and it covered a large area of the Niger Delta that would take over $500,000 in several years for other people to cover. The Ingenue RPMA, Random Phase Multiple Access technology, was installed for less than $200,000, $189,000. They installed this system. It took them 3 months. Over the next year, Shell Oil, who was responsible for this oil field, saved over $1 million in operating costs because of the ability to automate their operations in this field. So it's that kind of efficiency that you can get with this kind of technology. So these private networks have been installed. They've been out there since 2010, 11 or so, and all. Middle of last year, John Horn had been at T-Mobile and their machine-to-machine group, went to Rayco Wireless, built them up over 4 years, and sold them to Core. The middle of last year, he says, okay, what am I going to do now? I got some money, I've been watching the industry. He went to the board of directors for what was called OnRamp at the time, and he goes, guys, you're the best kept secret in the machine-to-machine world. I want to take you to the next level and get out of just doing these private networks. And they said, great, what do you want to do? He says, I want to do 2 things. I want to change the name. I want to change it from OnRamp, I want to change it to Ingenue. Innovation, Ingenuity, Ingenue. There you go. Okay, all right, great. What's the other thing you want to do? He said, I want to put your technology into public networks in 30 cities in the United States by the end of 2016. He made this, they said, great. He made this announcement in November of last year, and between November and the end of February, when they went to Mobile World Congress in Barcelona, they had representatives of infrastructure companies in 25 countries, mostly in the Asia, Pacific, and Middle East area, come to now Ingenue and say, guys, we've tested out Sigfox, we've tested out LoRa, some other technologies. They work okay as long as they're by themselves, but when you start trying to scale them up, they run out of juice. We want to license the RPMA technology in these countries. And we said, well, great. So between November and February, end of February, we had 25 countries that we signed up to install our network over there. So now we have 30 cities going in the United States in 2016, 25 countries underway. When I read this in January, I went, holy cow. The analyst that I've been following for the 3 years before that had said Ingenuity was a niche player. They're working at 2.4 gigahertz, the Wi-Fi frequencies. Everybody knows that can't go very far. So they're in oil and gas and utilities. They'll never go anywhere else, it looks like, so don't worry about it. When I read that they've got plans for putting in 30 cities, 25 countries, I went, there's a lot more here than anybody realizes. When I dug into it, what they are doing is they take the CDMA technology, they converted it a little bit, they call it RPMA technology now, random phase, and they're spreading the signal out, and they're doing a lot of processing gain. And what that means is they're manipulating the signal with an ASIC, application-specific integrated circuit that manipulates the radio signal and does a lot of calculations to it to spread it out over this frequency band, and I'll talk more about that in a moment. It enables them to have a very long distance with a very high link budget, which gives them long distance or the ability to penetrate deeply into buildings. They have, it's 175 dB link budget, which is 20 dB above anybody else's technology. Their receivers are highly sensitive. So that combination plus at 2.4 in the United States, Asia Pacific, and Australia, you can transmit at 4 watts EIRP, effective isometric radiated power. That's huge. So they're able to get, with all those different components, get very long range or very good penetration at 2.4. So they blew the analysts away. And they got 38 networks that are out there working, proving that every day. They also, because of the Wi-Fi frequency band has 80 megahertz, and I'm going to get that in more moment, but you got 80 megahertz to work with. That's a huge swath of spectrum to work with. We're able to do a lot of transmission, have a lot of capacity for transmission. So we can upload from the endpoint to the access point or base station 624 kilobits per second. And we can do 156 down, which is huge compared to these other guys. That allows us to download firmware updates and security patches. Nobody else can do that. And in this world right now, with all the security issues going on with your remote devices, particularly after Friday, that's going to become a much more important aspect of what you get with the system. The issue with the ISM bands, sub-gigahertz bands, are that they're not everywhere. So in the United States, you have 915 and 315. In Europe, you have 868 and 433. And then other places, you don't have access to any kind of sub-gigahertz frequency. So they're out of luck. There's nothing they can do. However, 2.4 gigahertz is in every country, the Wi-Fi frequency band, every country in the world. The beauty of that is that you're going to be able to create a product, an endpoint with our radio module in it, one board, one SKU. Now, the only thing that changes, United States, Australia, Asia Pacific allow the 4 watts EIRP. Europe, Middle East, Africa required to be 10 milliwatts. We just tune it down. The board stays the same. You just plug it in and tune it to the power level it needs to be. So that's going to be huge because it makes it easy. Now, I haven't talked about did I miss the cellular guys somewhere? Okay, the cellular guys, their issue with the frequencies is they have 44 frequencies that they have to keep up with around the world. So the module manufacturers can group them together by regions, but if you build a device for Europe, it won't necessarily, none of those 44 frequencies in every country around the world, so you can't have a universal product. So you have to create a product for this region, a different product for this region, a different product for here. So the one SKU from us would be a very big advantage. I don't know if you can see this or not, kind of gray. I tried to find a darker version and I couldn't do that. This is the Wi-Fi frequency band, 80 megahertz wide. The typical Wi-Fi frequencies are 1, 6, and 11. These are the non-overlapping frequencies that Wi-Fi uses. RPMA, Ingenuity, divides up this 80 megahertz into 1 megahertz channels. 1 megahertz transmit receive, 1 megahertz guard band, 1 megahertz transmit receive. So we have 40 channels out of this 80 that we can use for transmission. We don't we accept interference. Interference doesn't bother us. We just deal with it. It's not a problem. So they don't bother us, but if we're in the same building with them, we tend to bother their Wi-Fi system. But so we set up, there's a clear frequency at the bottom end of the Wi-Fi band. There's 3 between 1 and 6 that nothing's on, 3 between 6 and 11, and 3 above 11. So we'll start there, and as needed, we'll move into these other areas. But we're trying to play nice for right now. The beauty of this approach and the technology, this 1 megahertz channel here, San Diego Gas and Electric uses that for all 4,100 square miles of coverage because they're able to reuse it in every one of the access points. And one of the reasons they're able to do that is because random phase multiple access means when a signal is transmitted from an endpoint, if they're all coming at the same time to an access point, they're not really transmitting at the same time. There are chips of time difference between them. It's a random assignment. The ASIC on the receiver says, I see all these signals. I can do up to 1,000 simultaneous, what looks like simultaneous signals, and demodulate all of them at the same time. So this gives you incredible capacity and ability to absorb information that's coming in from your endpoints. If it gets above 1,000, 1,200 more, the system gracefully declines. Declines. Your access points on the outside have to then retransmit, but only until that time, until it happens. Until then will it happen. So the other aspect here about the technology is that we tightly control the power output of the endpoints. And almost instantaneously we can tell it to tune down or tune up whatever the power requirements are. And I'm going to talk about this more in the next slide, but remember that. It's tight, dynamic control of the power level. And that's going to make a big difference in the capacity of our systems. Then it's got all kinds of other technologies involved in it. Adaptive encoding, forward error correction. We can get blasted and have our signal wiped away and we reconstruct it. High receiver sensitivity. The other thing about 2.4 gigahertz, the quarter wave frequency is about 1 inch long. So when you compare 2.4 gigahertz to 900, any sub-gigahertz frequency, there's about 9 dB difference. These guys have an advantage over us of 9 dB. When you put diversity antennas in, 1 inch apart, now you're out of the null. One of the antennas is going to pick up the signal. Then you've immediately made up for that 9 dB difference. And then you got all the processing gain and the adaptive encoding and all the other factors that they use to improve the signal, and you get even much better range and much better penetration. And then it's direct sequence spread spectrum, so this is right out of what Qualcomm uses. And then it's got the high range. So a typical antenna cell site can go 10 miles. They talk about square miles of coverage. I converted that pi r squared equals the area. 10 miles range typically. Now that's going to depend on the environment you're in. If you're in an urban environment, you may be 2 miles. If you're in the highly dense vegetation area, you may be 2 miles. But if you're in a normal suburban area, you get 10 miles. If you're out in the boondocks and there's pretty flat land, you might get 10, 15, 20 miles in some cases. The problem with other approaches are that they have no sense of control of the endpoint power. So they transmit full power, worst case encoding scheme all the time. Sigfox transmits 3 times at highest power, longest time they can. LoRa, much the same way, they're transmitting full power. So what happens is, as you put more access points in trying to add to your capacity, you're actually getting into the receivers of all the other endpoints and access points out there, and it actually degrades the system. In our system, when an access point, we need to add another access point, we tune down the remote of power, and then we create small cells. And we just keep adding access points and making the cells smaller and smaller. They transmit at the lowest power possible, at the most optimum encoding scheme possible, so they're on the air the least amount of time. So we're able to add capacity. Every cell site that we put up, every access point, can handle 64,000 codes, 64,000 devices out there. When we run out of capacity, we add another access point, everything tunes down, we add another 64,000 potential devices to the system. If we get to a certain point where we don't want to add any more access points, and the more we densify these networks, the more the power can be used to get down into basements, equipment vaults, and deep into buildings. When we run out, and when we don't want to add more access points, then we've got two other ways to add capacity. We can start sectorizing the cell site. We can do 4 sectors, is how we're set up. So each sector will now have 64,000 endpoints that it can support. In addition to that, I talked about the 40 channels that we have available. We were using just one for the whole 4,100 square miles for San Diego. We can go to the next channel and add all that capacity again, and add another access point base station into the cell site. And we can just keep doing that until we get up to 40. So a tremendous amount of capacity available. So here's an example of, this is the Dallas-Fort Worth area. And so we have 18 cell sites up and working. We turned our network up here in Dallas back in April of this year. It designed for outdoor coverage with some indoor coverage. As we add more access points, then we'll be able to get, depending on where the need is, then we'll be able to get into the basements and the equipment vaults and whatnot. So we cover all of Dallas-Fort Worth, including McKinney, Denton, all of Fort Worth to the edge of Weatherford, all of Waxahachie, and Mesquite and Rockwell. In Houston, we go to Conroe, out past Katy, well down below Galveston, and all the Baytown or Bay Area out there where the refineries are located. In Austin, we go up past Georgetown and down Buda, Texas, out here to Lake Travis, and then out here almost to Elgin in their case. And then from San Antonio, we go up and meet them in San Marcos. And we'll fill in that area as need is in the future as well. And this actually goes down here to just about the Eagle Ford Shell. And we actually have a private network that we're converting. The oil company that services the Eagle Ford Shell system down here, Eagle Ford Shell Basin, has their own system that will eventually connect to this as well. And that system actually goes all the way over through College Station and to north of Houston. So we're going to have a very large footprint for that. Now, last topic, how much are we doing on time? So real quick, and I'll finish. Friday, I don't know if you watched or saw, the hackers have taken over a lot of Internet of Things, tens of billions of Internet of Things devices. And they use those devices then to create a distributed denial of service attack on the DNS servers for DYN, who provides service for Netflix and several other large companies. And because of that, it took them down, and they said, this is just the beginning. We're going to do it again and again and again. We, as creators of developers of end devices, need to be aware of this situation and create more security. Ingenu, our RPMA network, when we were working with utility companies, they said, you guys got to make this as secure and solid as possible. So there's 6 things that we do to make sure that we've got the high security, and now I'm done. Okay. So encryption is the first thing. You want that message to be confidential and nobody know what's in there. But the other thing is, you don't want somebody to capture, even if it's encrypted, if they capture that message and replay it because they understand that turns this off and that turns this on, then you're in trouble also, because if they figure that out, then they can do things with that information. Even though it's encrypted, they can replay it. So we don't allow that. We keep that from happening. You need to have mutual authentication. Not only are you making sure that what you're transmitting to is the right device, this device needs to know that it's receiving information from the correct. Because if you've got a man in the middle, he could be spoofing and making it look like he's the proper source. So you don't want that to happen. And then you want the devices to be completely anonymous. You don't want anyone to know what that device does, where it's located, and what its characteristics are and what it can do. Last slide. We do firmware downloads. Nobody else does. We want to make sure they're authenticated though, and make sure that that's properly, the proper information sent down. We want to make sure we support multicast. So if you have a whole line of street lights that you want to turn off in a group of town, you want to make sure that that's secure. That's a whole different thing than the individual unicast that we're sending out there. We make sure that's secure as well. So more information available. I'm on LinkedIn, at Hightower. I'm not the basketball referee. I'm in the Dallas-Fort Worth area. You know, don't you? And we have time for any questions?
Maybe one or two, but next speaker.
Yes, I know. Yeah. So thanks for coming, guys. I hope it was informative and you enjoyed learning something today. And if you have any questions, feel free to call me. My phone number is on the LinkedIn message. This will be posted, I think, right? The slides?
I can make them available if I've got them.
Okay, I'll send them to you.
Okay.
And it's Ed Hightower. Thanks, guys.
All right,